in. Welcome to the, I gotta click a button, looks like. Okay. Welcome to the ESIP IT&I and CDI Tech Stack October event. We're gonna let people kind of filter in here. I'm seeing the participant count start to go up now. Thanks for attending the October event. We've got a really interesting presentation. We're gonna have the folks from OpenTopography give us an overview of tools, data, and workflows. We have Chris Crosby and Matt Beckley from OpenTopography. I'm gonna go ahead and let's just say we are started at this point. So that'll give us that breakpoint of when you want to edit. All right, welcome to the ESIP IT&I CDI Tech Stack October presentation. Go ahead and go to the next slide. All right, so today we've got Chris Crosby and Matt Beckley from OpenTopography. They're gonna provide us with an overview of the NSF OpenTopography facility, the tools, the resources and data that are available, and some recent projects. We're really happy to have Chris, who's a co-founder and co-PI of OpenTopography, and Matt, who is a data engineer at OpenTopography, give us an interesting presentation on events, resources, and projects that they are undertaking right now. I've got just a quick intro and overview in my next slide, because one thing that I kind of wanted to look into, and I've got Rich Signell on as well, who really helped to kind of connect me with the CHS, that's the USGS Cloud Hosting Solutions Group. They have provisioned and stood up an RStudio server. So we have RStudio Connect, and they are working on RStudio Workbench. So what that allows us to do is actually publish your IPython notebooks, your R Markdown code, even your VS code, and then run that in a cloud-hosted server environment. So those of us that are with USGS can go ahead, and you should be able to, VPN in, click on that link, rconnectdev.chs.usgs.gov, and then that'll bring you into the RStudio Connect. If you go to publish, that'll then send a note off to the folks who are running the RStudio stack. Likely you'll get a response back from Courtney New, and she will then provide you with elevated privileges so that you can post and host your files and run them, and then share them from that environment so that others can also come in and connect and see. I see a couple shiny applications. I see a couple straight R Markdown, and I also see a couple really, really interesting dynamic IPython notebooks. Rich, did you want to kind of chime in on anything else? Since you're working with the Pangeo project, you've got the data dashboard, and I think you've been involved in this RStudio server as well.
Yeah, I mean, I guess the only thing to add is that I did try running, maybe this is a discussion we would have after the presentation too, but I did try running some of the notebooks just in a straight up, like in the ESIP Jupyter Hub. Yeah, if we install, we actually got some of the packages that were required built this week and distributed on CondaForge. And so we can install the environment there that will run these notebooks, but the final like cell, the 3D one that I guess it requires an X11 display or something like that. There's probably some work that needs to be done to figure out how to actually integrate that. I don't know if Philippe Fernandez is on the line, but he actually had some ideas about how we could make that happen. So anyway, but so it would be really cool to be able to just see this in any like Jupyter Hub, that is just that doesn't have necessarily the RStudio stuff, but just the ability to kind of install our packages if that's possible. I don't know. We'll see.
Yeah, and I guess the integrations are going to continue. So right now the RStudio Connect really lets you post your files, and then the RStudio Workbench actually gives you a full-fledged RStudio environment in which you can do your full-fledged data analysis routines. And I think that's kind of a neat, relatively unknown service that's available to those folks that are with USGS. I did want to also, open the conversation up to whether ESIP Lab had a similar AWS-based service that would allow participants or the community to run their RStudio or IPython routines. Does anyone know, anyone familiar with the ESIP Lab? Annie?
I am deeply familiar with the ESIP Lab.
Of course.
So is the question, Derek, basically like, how is there a mechanism to just for anyone in the community to say, hey, can we take advantage of the bucket of credits that ESIP has to experiment with things?
Yeah. Is there
yeah, I mean, that's Rich has tapped into that unspoken opportunity many times to be able to just like, hey, could we just try things out, because it's an environment that is outside of the kind of federal guardrails and able to kind of just try things out. There hasn't been an official like solicitation or opportunity where I like make an announcement. Hold on. Can you mute over there? My office mate is also listening to this call. But at this point, it's kind of been a one-on-one basis. Like you say, hey, could I use some ESIP resources? I get a basic idea of what budget you have. I'm actually just reapplying for our next bucket of credits right now. So I would say as of now, just give me a call, but we haven't felt the need, or I haven't felt the need to formalize it too much to this point because we haven't had an onslaught of requests. So I would say just be in touch.
Okay.
I mean, it could definitely be done, right? Like, because we have the full Amazon cloud, you know, we don't have the restrictions that we have even at USGS or NOAA or whatever. So, yeah.
Yeah, so one of the opportunities that I do want to explore is the fact that we are provisioning our data and APIs for the National Geospatial Program into AWS buckets. The fact that this cloud-hosted RStudio solution is also available. We're really thinking that that will then provide an opportunity for us to have our compute and our data essentially sitting side by side. So you're not dealing with that traditional bottleneck of going through your gateway, then another gateway, then grabbing that, and then bringing that down into your environment. So Rich, I'm hoping that between you, myself, and a couple others, we can kind of test out that hypothesis.
Yeah, no, absolutely.
And,
I mean, and we've been doing this on the Python side for a while, but it's nice to kind of start to get the R users, the same kind of approaches going for those guys too.
Awesome. Thanks, Rich. Thanks for chiming in. Thanks for participating. All right, next slide. I think we're getting ready for the presentation. So with that, we've got Chris and Matt up, and thank you so much, Chris. Take it away.
Sure. Thank you very much for the invitation, Derek. Derek and I chatted last week about this presentation a little bit, and so I think the emphasis here is going to be on OpenTopography, but actually a lot of people I see listing the participants are familiar faces, and so probably have heard me talk about OpenTopography or heard one of us talk about OpenTopography in the past. So what we're going to try to do here is focus on OpenTopography as just a quick overview for those of you who are not familiar, but really try to emphasize ways that OpenTopography is leveraging USGS 3DEP resources, and specifically some of the cloud native work that's been done recently over the last couple of years, and how we're kind of trying to leverage that infrastructure, that migration to the cloud, and to pipe these data sets through OpenTopography. So Matt Beckley, who's also on the call, and I are going to kind of trade off and talk about various topics in this agenda here. But basically what we're going to talk about is OpenTopography access to 3DEP point cloud and raster data via cloud, these cloud native resources, and some of the national map API infrastructure. I'm going to show you an example of using that same cloud native data sets to do some big data processing. This is like looking at topographic change of at sort of the state level scale. So I'm going to show you an example from Indiana of that. And then the last thing is this Rayshader Jupyter Notebook that we built this summer. An intern working with Matt and I built this summer, and that also leverages the national map APIs to pull in data and generate these Rayshader visualizations. So that's the plan. I'll try to go pretty quickly through the OpenTopo kind of overview because I think a lot of you are familiar. roughly with what OpenTopo is all about these days. So OpenTopography is a project that's funded by the National Science Foundation with the goal of democratizing online access to high-resolution topography. So we got into this in the kind of mid-2000s when airborne LiDAR was still a new technology, and the National Science Foundation was investing a fair amount of money through projects like EarthScope to collect LiDAR data sets of active faults and other sort of interesting tectonic and geophysical kind of features in the Western United States. We've since expanded to emphasize other types of data sets such as photogrammetry, as well as kind of what we call kind of global topographic data sets. So these are things like, shuttle radar topography and other kind of relatively common geospatial data sets, and we make those available through OpenTopography. And one of the things we've been doing from the beginning really has been an emphasis on co-location of data with processing tools to allow users to derive products. So those could be visualizations, it could be creating their own custom DEM type products like digital terrain models, digital surface models, could be contour line generation. And so this has been something that I think has become relatively commonplace in the geospatial, Earth observation world, is to start thinking about how we do this. But we started doing this, in the mid 2000s. At the time, it seemed sort of novel. And so, as I said, OpenTopo was first funded in 2009. It's a collaboration between San Diego Supercomputer Center, UNAVCO, where Matt and I work, and Arizona State University. We're a small team. This is it. These people in the photograph are basically the extent of OpenTopography. We have a new postdoc who just joined us, who isn't in the picture. I know Vishu Nandagam, who's the lead at San Diego Supercomputer Center, is lurking somewhere on this call. So if there are technical questions towards the end, we'll pull Vishu in. And importantly, the funding for OpenTopography comes from the Division of Earth Sciences within the National Science Foundation, very specifically the Geoinformatics program. So OpenTopography is a data facility funded through Geoinformatics. And so a lot of what we do is really oriented towards earth science facilitation, research facilitation, education. But as we'll talk about, OpenTopography has actually become a pretty widely utilized platform for people interested in accessing topographic data, well outside of the academic world. And so that creates some interesting opportunities. It also creates some interesting challenges, which I'll briefly touch on at some point later in the presentation. So we basically, it's fundamentally a portal or a clearinghouse type of interface with a GUI that provides access to both raw data, whether that's point cloud or raster type products, through to derivatives. So, and these are things like visualizations, other geospatial data products like contours, things like that. And a lot of the access is invoked kind of on demand. So instead of pre-computing types of products, we generally just host the raw data and we put compute next to it and services next to it, and then let users can interact with the interface to access the data that they need. And again, the goal was trying to strip out a lot of that kind of middle skill set and resources and tools that a user would need to get to the product they want. So, the original motivation was something like an earthquake geologist who wants to go map the San Andreas Fault, literally like on a hillshade printed out on a clipboard. They don't necessarily want to learn how to interact with LiDAR point cloud data. And so we built the process and workflow to allow the person to derive those products entirely online in a web-based environment. And that's still largely the motivation, is to make the products easy to use, easy to discover, and to give people kind of what they want, as opposed to delivering them raw data. Although the raw data is always available. We have other pathways to access data. There's the web portal I just mentioned. There's APIs, web services, and we are doing a lot of work with bulk data access through things like cloud optimized geotiffs and other kinds of resources. So, in terms of services, there's the topographic data itself that's sitting in various kinds of resources, and then there's tools to subset and filter those data sets, whether it's on the point cloud or the raster data. And then a set of processing services. So we do browser-based visualization of point clouds, dynamic generation of gridded products from point clouds. So that's digital elevations of models of various kinds, whether it's a DTM, a DSM. We have tools for canopy height calculation, sort of raster-based visualization like hill shades and slope maps and kind of the classic raster-based topographic products. We do dynamic generation of contour lines from topography. And then a big emphasis, which I'll show you an example of a little bit later, is we started working on tools for topographic differencing, because increasingly we're getting to the point where some parts of the world are getting covered by multiple collects. And so you can start looking at multi-temporal change and how the landscape's moving. We've actually done this we have two sets of tools. One is for vertical change. So this is just essentially raster subtraction, change in the Z direction of the landscape. So what's going up, what's going down, erosion, deposition, anthropogenic change. And then we have a sort of more focused tool that's on 3D differencing. And this is essentially calculating how pieces of the landscape translate in 3 dimensions. And so as opposed to just the Z direction, this tool is really cool. It's taken a lot of work to put together, but it's pretty specialized. It's mostly oriented towards earthquakes, where the landscape translates oftentimes, like a strike slip type of earthquake event. Works pretty well on landslides sometimes, as long as the landmass sort of stays relatively coherent. And so these are 2 sets of relatively new tools. And then the last thing that we do is hydrologic routing. So we've taken Tau DEM, which is an open source flow routing tool, and put it on the HPC resource at the San Diego Supercomputer Center, and allow users to do dynamic flow accumulation and basic hydrologic routing through the portal. So that's kind of the set of tools. I'm not going to show you what the OpenTopo interface looks like, because it's a web GUI. Everybody should be pretty familiar with what those look like. If you want to play with it, OpenTopography.org is the place to go and check it out. And so for the rest of the presentation, we're going to talk more about utilizing 3DEP services, USGS 3DEP services. So this is basically direct access to point cloud data that's currently hosted in an AWS public data set. And this is in a cloud data format called EPT, end-to-end point tiles. Another thing we recently did is we're now pulling 3DEP raster products. So the 1 meter, the 1/3 arcsecond, and the 1 arcsecond DEM data all into OpenTopography. And those are also leveraging Amazon published cloud optimized geotiffs. I'm going to talk about this topographic differencing use case. And then we're going to talk about this Rayshader notebook that we put together this summer. And the kind of common theme here is USGS's sort of cloud native services, data and services. So one of the initial things about OpenTopography that was always sort of challenging was we had this platform that provided a lot of services on top of data, but we actually didn't have that much data. Because our funding comes from the National Science Foundation, we really were focused on these relatively small data sets that were collected for earth science research applications. So this is a map showing the data that are inside of OpenTopography that are hosted at the San Diego Supercomputer Center. It's a lot of pretty small polygons. We don't have wall-to-wall coverage like you get through the 3DEP program currently, with a few exceptions. And so the state of Indiana was an early partner of ours and asked us to host their data set. And so we've got the 2011, 12, 13 statewide LiDAR data set from Indiana. And then more recently, we started working with Land Information New Zealand as a national mapping agency in New Zealand, and they're using OpenTopography as their distribution platform for their nationwide LiDAR program. So their lenses national LiDAR program looks a lot like 3DEP. It was modeled after 3DEP. It has very similar documentation and formats and everything, just like 3DEP. So all those data are ending up in OpenTopography over the next 5 or so years. And so we actually have great coverage in New Zealand, which is nice. But the challenge has always been, people are always like, this is great, but I wish you had data in my neck of the woods, or where I'm doing my research, or where I'm interested in accessing data. And obviously 3DEP is the big giant in the room, right? Where in the process of collecting nationwide LiDAR by 2023, something like, I don't know if one of you can tell me, but I think it's something like 70+% of the United States is covered now. This is the status map that I just pulled off the web for FY21. And this is great, but until recently, these data sets were not easily accessible by groups like OpenTopography to sort of federate and pipe through our pathways. And so in 2019, there were these 2 big efforts within the 3DEP program that we're happy to take advantage of. And this was to basically take the point cloud data as well as the raster topographic products and publish them into Amazon buckets as cloud optimized geotiffs for the rasters and as endpoint point tiles, which are the point cloud version. The point cloud data is available as a public data set, so free to access and free to egress. And then there's also a user requester pays bucket that has the point cloud in the LAZ format. And so what we've done over the last couple of years is to basically take these data resources and pipe them through the OpenTopography discovery and processing pipeline, with the goal being to essentially leverage these and to provide our users seamless access to this data, make these data easier to discover, specifically also to allow people to apply the OpenTopography processing tools for generation of derivatives. So it's the same set of processing tools applied to the data that OpenTopography hosts, the red polygons in that previous map, but now we can do it for anything that's inside of the 3DEP program. And this is basically just a value-added service that we're applying to the data. And again, the goal here is to encourage people to do interesting and creative things with these data by making them easier to use, whether that's science, whether that's education, whether it's all kinds of broader impacts. That's the motivation. And so that's kind of, now we're going to show you a little bit more about how they've actually done this in terms of the technical implementations. And so I'm going to hand to Matt and let Matt start talking about the next couple of slides.
Okay, thanks, Chris. So this slide would be kind of like maybe a broad overview of how a typical user would access USGS 3DEP data through OpenTopography. Most users, and especially for the 3DEP data, they're accessing it through the web map portal. So they would go to a landing page and draw an area of interest on a map. And then from SDSC, we would do a call to that Entwine bucket. And then again, as Chris mentioned, Entwine is sort of a cloud optimized point cloud format for point clouds. And so Howard Butler set this up with his group in conjunction with the USGS. So the call goes out to that bucket, and then we return an LAS or an LAZ file. And then once we have that file, depending on what options the users chose, we have the whole suite of OpenTopo tools available to us. And so users can do things like gridding the data, visualizing, contouring, creating further different raster products. And I'll talk a little bit more about that in the next slide. So this is more of a under the hood, what's actually going on to enable 3DEP access through OpenTopography. So as I mentioned, Howard Butler set up this bucket in conjunction with the USGS. He also has a GitHub site where he does the processing of that data. And as part of that processing, he creates a JSON file with boundaries for each 3DEP data set as it comes in. So with OpenTopography, we sync with that resource, and anytime a new boundary comes in, we download the boundary and we download all of the EPT files, and then we run our own QA QC on that data. So we do things like check for vertical datums. Are they all the same within that one data set? There are cases where they haven't been, thankfully not often, but it's kind of a critical thing to check. We also download the metadata information from the USGS geo packages. So that's kind of critical too, because for each data set, we create a data page, and we also always want to link back to the USGS URLs that contain the actual metadata for that data set so that the data provenance is preserved for each data set. We also extract the appropriate UTM and state plane coordinate system for each data set. The Entwine data sets as they're hosted are in WebMercator, which is great for web mapping, but not very useful for actual data analysis. So by having it in these two projections, users can reproject the data into those UTM and state plane zones. We find most people use the UTM projection for their analysis. And then we also sort of scrape out some other statistics such as point densities of the data, maybe some classifications that are in the LiDAR data set. And so then once we have all of that, those boundaries and that metadata are loaded into our database at OpenTopography, and a landing page for each data set is created so that when a user goes to a landing page for a new 3DEP data set, they'll see the metadata specific for that data set. And so once again, on a map, they'll just draw their area of interest. And what that does is spawn a PDAL query. And so that PDAL query goes to that Amazon bucket and extracts the LiDAR data for that region, and then returns an LAS or LAZ. And then once we have that, we can do all kinds of our secondary products, like create 3D point cloud visualizations, which is what you see here with the Statue of Liberty. This is visualized in the Potri 3D visualizer that is accessible through OpenTopography. You can also do things like contours, which is a new feature we just added. You can create visualizations, you can grid that data. So once you have that LAS file subsetted, you can do anything you can do within OpenTopography. Next slide, Chris. So a separate workflow and a separate product, this is a new thing we released last month, is access to the USGS 3DEP project-based and seamless-based rasters. So these are things like the project-based 1 meter raster product and the 1/3 arcsecond and 1 arcsecond raster products. We were initially going to take the approach of just kind of cloning and mirroring the data. So we actually downloaded the entire 1 arcsecond catalog and created a page that way. And it runs fast, but you kind of run into the issue of as data sets get updated on the USGS side, we'd be out of sync. So then we'd have to write a script to sort of make sure we're in sync with USGS. And so we decided to take a different approach and do a more dynamic sort of API access. And so this is the workflow that's detailed here, and I'll talk through it. It's a similar situation. We have a landing page for each of those 3 products. So you have a landing page for the USGS 3DEP 1 meter, 1/3 arcsecond, and 1 arcsecond. The user will go to the map, draw a bounding box. Instead of downloading the data locally, how we would do in the past, now that's spawning a call to the USGS National Map Products API. From that, it will return a JSON file of the URLs of all of the TIFF files that intersect that box. So now we have listing all of the data files that are in the cloud, and we could build a VRT, or a virtual raster data set. That's a GDAL, not specific, but GDAL provides that format of those files. And with VisiCurl, you then create this document that has all access to those, dynamic access to those files. And then with the GDAL tool, you can actually, on the fly, subset that VRT and return basically just the single mosaic DEM for that region. So that GDAL call will actually go in and subset each of the DEMs that's listed in that file. And this would work whether it's a cog or not, it would still do that. But the fact that the USGS then did the great thing of converting to cogs, that really increased the performance of this. So now instead of having to go through and read through each one of those TIFF files in that list, could be tens, could be hundreds of files. It goes in, just reads the header, finds the piece of data that it needs, takes it out, goes to the next file, and then mosaics them all together. And then the user ends up with just a single mosaic DEM for the area they want without any intermediary file. So it's been working quite well. The one issue is that this is sort of reliant on ScienceBase. So if ScienceBase is down, the product API is down, and the whole workflow is broken. So we've had to put in some checks to check the status of ScienceBase. And if ScienceBase is running, users have access to this. So we put in a check so that users don't have to go through and create failed jobs. So they'll know if ScienceBase is down, they won't be able to run it. Next slide, Chris. So another complication with this is, well, not complication, but interesting problem is the 1 meter DM is a collection that is continually growing. And so the spatial bounds of available data sets is constantly growing and changing. So we've put in a script that downloads, excuse me, the geo package for the 1 meter DM that will get the latest spatial bounds of the 1 meter DM. And then we sync that nightly with what we have. And so we're constantly updating to make sure that we're providing a map of the latest 1 meter coverage. This isn't an issue for the 1 arcsecond and 1/3 arcsecond because those spatial bounds are fixed. It's all of the US, in some cases for the 1 arcsecond, all of North America. But for the 1 meter, we have to do this dynamic check. So we're downloading that geo package nightly to make sure we're up to date. I think that was, yeah, I'll turn it back to you, Chris, for these next two.
Yeah, thanks. So that's the sort of under the hood of how this actually works. So just a quick sort of status of this exercise. So the point cloud data have been available through OpenTopography since early in 2020, I guess, in OpenTopography. And then, as Matt said, the DM data is a recent addition. And so there are 33 trillion LiDAR points available in the 3DEP catalog right now, and they're all available through OpenTopography, which is amazing. And it's really been quite awesome. One of the problems is that, and I'll talk a little bit more about this in a second, is that we've found in OpenTopography, as you introduce more data, you introduce more users. And so the potential for 3DEP is really powerful and amazing, but also the potential to sort of exceed what OpenTopography is resourced to do is also challenged. And so what we've done initially is sort of the pilot for rolling these out is we've restricted access to this functionality, the point cloud access, as well as the 1 meter digital elevation model product to our academic community, because that's who NSF funds us to support. And so if you've got a .edu address, you're able to access this. We also just launched a application for international academics and other kinds of educators who don't necessarily have a .edu account. So there's a little over 2,100 academic users who in the last under 2 years have signed up to utilize 3DEP. They've run 96, almost 9,700 jobs. And this is 10 data sets that people are hitting within the point cloud bucket. So kind of interesting. Los Angeles, Southern California in general is pretty popular. New York City, perhaps not surprisingly. But we have metrics on utilization of every single resource in that bucket, all 1,628 3DEP data sets sitting in that bucket, because we're keeping track of who's querying against which. And so this is interesting. And then I guess the other comment here is that we're pulling this data across the wire from San Diego Supercomputing Center. We go to the bucket, which I think is US Amazon West, and pull it back across. So there's actually some optimized networking between San Diego Supercomputer Center and Amazon, it turns out. Some dark fiber connections that make things go a little bit faster, but there's the run times of jobs against 3DEP data are longer than if the data were hosted in the data center at San Diego, which is logical. Just to say a little bit more about this issue of the restriction. So we've been hosting this Indiana data set since I guess 2013 is when we put that in. So we have really interesting analytics on what happens to a really large scale data set. And so Indiana statewide by itself has seen this pretty impressive growth over time. On the lower left is a heat map showing where users are querying that data set. So the spatial distribution of interest in the data set. We know who the top users are, we know where they come from, and we also know how many jobs have been run. So just this data set alone has seen 41,000 jobs run. And so if you extrapolate this utilization to 70+% of the United States, it's in 3DEP. We're pretty confident that OpenTopography is not funded by the National Science Foundation well enough to basically open this up nationally to any user on the internet. And honestly, the National Science Foundation isn't necessarily interested in paying for that either. And so this is a bit of a challenge that we've been navigating. So we've, as I said, have this .edu restriction, and we're exploring opportunities to come up with some new resources to enable more open access to this. This is an ongoing conversation basically about sustainability of OpenTopography that's happening right now. With us, with the National Science Foundation, and we're trying to think creatively about this. So that's the kind of access to these data sets inside of OpenTopography. So now I'm going to move on to another topic and show you an example of another thing we've done with these resources, these data. So as I said earlier, one of the things we've been really interested in recently is building tools for calculating change. And so here's a very simple example that we use all the time. This is White Sands National Monument in New Mexico. This is a very active dune field, and we have 2 airborne LiDAR data sets that were collected for academic research purposes by the National Science Foundation through the National Center for Airborne Laser Mapping. Less than a year between these 2 data sets, September 2009, June 2010, you can calculate, as a very simple raster calculation, the difference between them. And in the panel on the right there, you can see the difference. And so this is blue is accumulation of sand, and red is erosion of sand, basically. So the down versus upward motion in the landscape. Dominant wind direction for White Sands is from the southwest, and so you can see these dunes marching to the northeast. All right, so this is just a very simple example of illustrating what this calculation looks like. So To do this effectively, though, you need to basically go back to the point clouds. And so what we do is we go to the pre-date, that's what we call pre or post data set, the bounding data sets. Typically, they have different point densities because the older data sets in general with LiDAR data tend to be lower resolution. We rasterize to the exact same grids so that we don't have to deal with half pixel offsets between the grids. And then we subtract them, right? So this is the process. So to do this, you have to go back to the source data. And so what we've done to demonstrate this at scale is we computed the topographic change of the whole state of Indiana just recently. And this is actually ongoing work. We have a manuscript we're working on right now about this exercise. You might ask, why Indiana? Indiana is actually maybe not that interesting from a topographic change perspective. It's maybe not the most dynamic place in the United States. But we did it because we had an pre-existing relationship with Indiana because they asked us to host their data from the 2011 to 2013 collect, which was not a 3DEP data set. And they just completed another 3DEP collect of the state. So there's basically roughly decadal bounding data across the state of Indiana. And so this is an interesting exercise. We did this mostly just to prove that we could and to think about what the implications are for state levels or even national level scale topographic change calculations. Because once 3DEP is complete, you should be able to start thinking about doing this. If we do 3DEP again in 5 years, 3DEP again in 10 years, you should be able to do this nationally. This turns out to be non-trivial. Indiana has 36,000 miles. So you can't do this manually. So this will be automated, this whole process. It's a big data set. The final product, so what we basically compute is a DTM, a DSM, and the change between those for each. So we have basically a DTM, a DSM for the earlier data set, a DTM, and DSM for the later data set, the change between the DTMs, the change between the DSMs, and we also calculate a canopy height for both of them. So it's 4 terabytes of data. And we figured that if you do this on like your PC workstation or something, it's going to take about a year of compute time. And there's also some subtleties about coordinate systems and making sure that you're not conflating different datums and things like that in here. And so we're doing this by hitting, again, that Amazon public dataset bucket that contains the EPT data. So the way this works is the same cartoon. We go from San Diego over the bucket, we pull the data out, we get point clouds back, we grid those point clouds into a consistent grid origin. So the grids are aligned. Also in this process, going point clouds to DMs, we're backing out the various coordinate system issues, solving for that, and then we compute the difference. So I'm going to show you now is just a couple examples of what this actually looks like. So here is the digital surface model difference for the whole state of Indiana. And there's some things you see in here. If you're used to looking at LiDAR, there's some really interesting things you see in here. But the obvious signals in the digital surface models, this is the top of the canopy, buildings, et cetera, are things like agricultural change, rivers, quarries, mining operations, and urban development. You also see a pretty significant seasonal change due to the fact that the LiDAR data sets were not collected at the exact same time. So you may have a leaf on versus a leaf off type of situation. And that's quite common as well. Again, the color bars on all of these are the same. So blue is upward change, red is downward change in the topography. Here's the digital topographic model, or sorry, the digital terrain model. So this is the essentially bare earth topography. And you see essentially the same things. You also see, though, if you're looking at this, a lot of striping. And that striping is scan line artifacts, so misalignments between swath to swath scans. You can also see that the data sets were collected kind of in these different orientations as a function of where they were flying and what polygons are being collected. We think this is largely in the earlier data set, not the 3DEP 2016 to 2020 data set. We think it's primarily in the earlier data, although we haven't dug into the error sources as deeply yet. It's on our list of things to do. But it's an interesting demonstration that the ability to detect change at this sort of meter resolution is basically only as good as the source data, right? And so if you wanted to fix these errors, you could do so, but it'd be very manually intensive to go back and sort of fix the swath alignments between the laser scans. in that earlier data set. And so this is something we haven't done, we don't plan to do. This exercise was mostly to illustrate some of these issues and the fact that they stand out quite prominently when you look at the whole state. So 3 or 4 is quick zoomed in examples, since looking at the whole state is sort of different than looking at this on a case-by-case basis. So so these next couple sets of slides are basically on the left is going to be a flicker between the two either DSMs or DTMs that we're looking at, and then the right is the change map that's computed. And all of this is, we did all this these change calculations at 1 meter pixel resolution. So so this is urban, like sort of housing development outside of Indianapolis. So just, again, I'm showing you examples of what you see when you start digging around in this data. Another example, this is a quarry outside or near Louisville, Indiana. These are quite prominent signals because they're moving a lot of material around, right? Stockpile volume change, things like that. So they stand out. What else is in this set? Oh, here's the Wabash River, a nice meander in the Wabash River, where you can see the changing fluvial geometry. So it's a good fluvial geomorphic example. This is also interesting though, because you can see one of these swath alignment issues in the middle of the difference map. So you can see there's a darker red in the middle there in the center of that meander, and that's this issue of the quality of the data sets and the alignments. And then the last one is at the Indiana Dunes National Park along Lake Michigan, where actually this is a coastal change example. And it turns out that this spot in particular is actually the change in the shoreline is actually a big deal right now in this part of the world. And this was a PBS NewsHour special about this problem that ran actually in early September. And so you can see it quite clearly in the topographic difference. So that's an example of like sort of big data computations. We're not doing this through the OpenTopography portal, but we are leveraging that cloud native EPT bucket that holds the point cloud data to do this. You might ask, how much of this could you actually do in the United States? So we did an exercise where we looked at the 3DEP catalog as well as the data sets that are inside the US Interagency Elevation Inventory to try to figure out how much of the United States currently has some kind of high resolution topographic data available, LiDAR available, that could be used to do these kinds of things. So any place that is black on this map of the United States is a spot where, in theory, you could access at least 2 data sets and do a difference between them. That's not to say that all these data sets are particularly good or that they're easy to access, because some of these data sets might be county or something, but they're just entries in the US IDI. So we think it's possible over roughly a third of the lower 48 right now. But this was just done as an exercise to see what it would look like. Obviously, as 3DEP rolls out and as more data become available, this number was going to increase. So that's the differencing example, again, leveraging the EPT buckets. And then the last thing to talk about before we wrap up here and go to discussion is this Rayshader notebook that we'll talk about.
Okay, thanks, Chris. So Raciator, not that I was that familiar with Rayshader, but this, for those of you who are not familiar, including myself, it's an open source package, and it uses the R programming language, and it produces these really cool 2D and 3D terrain visualizations. And we've had some users at OpenTopo that are using it and creating some really amazing visualizations. So this summer we had our intern, Nat Quinn, who was very good at visualizations. He looked into creating a Jupyter Notebook that would work through a typical Rayshader workflow and how to produce some of these terrain visualizations. So he did that over the summer, and we have that notebook on our GitHub site. And we also, as part of that workflow, you sort of enter a lat long box, and it sort of zooms to an area, and then it leverages the sort of USGS 3DEP image service. So it goes in and grabs a DEM for whatever region you select, so it downloads that. Then it goes to the ArcGIS image server and downloads the aerial imagery or satellite imagery for that same region, and then it drapes the imagery on top of the DEM and makes this visualization. Next slide, Chris. So as I mentioned, it's a fairly simple notebook, but it can produce some really cool visualizations. This image here is the Kings Range in Northern California. And it is leveraging that USGS sort of web service to get the DEM for any area that the user enters within the US. What's cool about the Rayshader thing is you can sort of tweak different parameters. So you can do different lighting angles, different terrains, different textures. You can flood your model to see how flooding would affect it. Next slide, Chris. And so for those of you who are not familiar with Jupyter Notebooks, this is just sort of a little snapshot of what it looks like. Notebooks are particularly advantageous for working with Rayshader because, as I mentioned, there's a lot of different parameters to tweak and you might not sure how your visualization will look. So as you can see, the code is all in these cells and users can execute them, or they can go in and tweak the parameters themselves, rerun the code, change a viewing angle or change a parameter and see what that visualization looks like. So it's really advantageous for this type of work, this interactive playing with the data. So this is this is an R notebook, so it's using the R kernel within a Jupyter notebook environment. Sometimes that's difficult to set up, so we also provided the R Studio code, which is also available. And to, I think it was Rich's comment before about having some issues with the X11, we had that issue ourselves. Our intern was actually we were both working on Macs. We had different versions of X11, and sometimes that was a little bit of an issue with the 3D visualization. But for the most part, at least on my computer, how the notebook is now, it works and runs, but we could always work with USGS if they want to put it in their environment to try and get that working properly. So yeah, our intern spent a lot of time working on this and really produces some really nice visualizations. We put a lot of them on a blog post that's on the OpenTopography site. Back to you, Chris.
Yeah, so I think essentially that's that was what we wanted to highlight here. So just a couple conclusions I think here are that these, the USGS 3.0 web services and the cloud migration to cloud native formats have really allowed us to do some what we think are interesting things to leverage these data and make them available to our community. And we're pretty invested in trying to increase the return on investment in these data and to explore some of the opportunities for things like computing statewide difference on the data. We'd really love to make this data available to everybody through OpenTopography, but again, the resourcing is something we're working on, trying to come up with a sustainability plan for how we're going to do that. And then just that these services are great, and the stability of them is what makes this possible for us. And so as Matt said, there have been some issues recently with Sciencebase being down, and that has impacted the ability for us to consistently deliver this data to our users. And so I think that's just sort of an interesting comment for the USGS folks, is just that, as you start putting these data out there and these cool resources, it's really powerful. It really enables really exciting things, but it's also, there's a need to make them reliable as much as possible. And so that was it. We're willing to take some questions, or there's definitely been some discussion in the chat, so we can tackle some of those maybe here as well. So
yeah, Chris and Matt, thanks so much. And you can see that we've accumulated some questions in there. Some of those may have been answered, but I really want to give those that have asked questions first in the chat, first shot at kind of a Q&A with Chris and Matt. So looks like we're going all the way. Kim started this. Kim, did you get answers to your questions, or did you want to kind of jump in and ask a couple of these? Yep.
No, I absolutely got answers on my questions. I do have one, and this is very specific. I like that you're providing feedback so real quick, I'm just going to explain why I'm asking you, so you have context. I used to manage 3DEP operations at NG Talk. I'm the deputy director there now. So whenever people are noticing, things in QC on our published data, I really like to know where those errors are, feedback for our process to make things better. Obviously, it helps all of us out if we can catch this stuff upstream. So that's the context of the question. I'm curious if in your integration with this data, if you have specifically come across and noted on GitHub, Howard's GitHub, any systematic misclassification issues on classifications other than ground. What I'm looking for specifically is misclassified, unclassified points, basically noise being retained in the data that would bust your DSM and your surface modeling.
Yeah, unfortunately, I haven't dug too deep into the classifications, and I haven't noticed that. The main thing I notice is just like spatial thing. There were a couple issues where vertical datums were using, like one was using a geoid 3 versus a geoid 12 or something like that. So we kind of flagged that one. And to answer, number one, to answer your question, any things I find, I report in Howard's bucket. And this, again, I don't know in the workflow, this could be on Howard's end of processing. I'm not sure. It might be fine the USGS side of things. So, there's also that. The main issue I see is sometimes data sets, they seem to be just projected wrong. Like a data set will plot in the wrong place, things like that. And there's been a handful of those that I've sort of reported. That seems to be the most common thing. I can't really speak to the classification. I haven't dug too much into like if I've seen misclassifications.
No, that's fine.
There definitely are data sets that have a lot of noise in them that seem to, but I haven't looked that closely if they're accurately classified or not. But there's definitely some data. I've had users send emails to us that say, "Hey, what is going on with this data set? I just got from,
the Tacoma." I remember the Tacoma one, the one in Seattle. We looked at the Tacoma Bridge, and it was like a ton of noise, and we're like, I don't know what's going on with that one, but
yeah.
Okay. No, that's really good to know.
And like the other point is that that differencing of the Indiana thing, we didn't look at the quality of the classification. So some of the others, there's definitely some. If you look closely at the difference map there's some places where maybe the classifications are wrong. But again, we haven't tracked. I don't want to blame that on the 3DEP data because actually I think the earlier Indiana data set's kind of ugly.
Oh, and I would say like it's not a question of blame either at all. Like this is a constructive feedback for everyone across the board. We're constantly looking to see how we can improve our processes, and where things are getting missed. And we do a lot of stuff with GDAL VRTs. So you're probably noticing some really pointed questions from me, just making sure that we're on the same page as everyone else. I guess my other question, and this is something that could be taken offline because I could ask you questions for the rest of the afternoon, is do you anticipate as we go to NatRef 2022 or 2025, whatever that is now, you are going to have that time datum in there. Do you think that is going to cause problems on your workflow, since you mentioned differences in datums with building your standardized VRTs off of our standard product? I'm just curious. Like, you don't have to answer that now, but that freaks me out. So
I don't blame you. I'm always shocked at, my personal thing is like, we do topography, a lot of people do topography, and I'm always shocked at how vertical datums get kind of swept under the rug sometimes when it's like the kind of the core of your measurement. A lot of reporting, not in USGS, but in general in the community, I find sometimes vertical metadata on the vertical datums is sometimes lacking, and I find that a bit shocking. So I think people that needs to improve for sure.
Yeah, and the coordinate system thing is totally again, a huge issue with these multi-temporal analyses, and something that we frankly haven't fully dove into yet, but we need to, and it's definitely on our list of technical things to work on is to deal with the full suite of ability to reproject data and realign data, both the legacy data, but anything coming down the road. And I think I saw Evan. There was a question about this earlier, right? Somebody asked a question.
Yeah, if we want to go through that list, then we've got Evan and Rich. Yeah. So I think that answers. Evan, did you want to chime in, Evan?
No, that
okay.
Is my question. Thank you much. Yeah.
All right, and then Rich was asking about spatial temporal asset catalogs. I see that there's some back and forth between that. Rich, did you get your answer?
Yeah, I just mentioned that because with the science-based dependence, that that would I guess it would maybe do two things. It would be kind of unify the way we search for like imagery and topography, maybe, or and sort of heading towards hopefully some universal way to kind of search and cloud analysis ready data or whatever, and then and then also take away that dependence on science base.
Yeah, and that's a good point. I haven't really explored the stack catalog to see if it has what we need. It probably does, and that would be nice.
We actually we have published the OpenTopography data in the stack catalog as well. And I think Howard has produced a stack for 3DEP, so definitely worth looking. I think the point cloud profile for stack I think it just became a stable version 1 or something. So it's definitely worth looking at again.
Cool.
All right.
Thank you.
Yep. And then Toby asked, can .gov addresses have access to the 1 meter data? So can we join the .edu folks? Can we get free Prime too?
Those data sets are, we're just re-delivering data sets that are accessible via several other pathways, right? So it's not like those data sets aren't accessible to .gov addresses. If you want them to be accessible through OpenTopography, you need to have a conversation.
Toby, did you want to chime in? All right. Then the kind of, yep. Somebody want to say something?
I was just going to say, to follow up on that point, that we've actually, our program officer at the National Science Foundation has talked to folks at USGS. I don't think people inside the kind of like in the more of the national mapping program, because there's been some interest in accessing open topo services for that program. And the conclusion from our program officer was that some sort of interagency collaboration was going to be complicated and hard.
Okay. And
that probably wasn't the way to solve the problem.
And Chris, we're always looking for ways to efficiently manage and handle data. So, I think we've been talking about this since like 2010 with the Tahoe data collection. So it's just always looking for those opportunities. So it's always one of those things. I'd rather ask you tell me no than otherwise.
Yeah, Toby, and this is Jason. I've been passing the hat around for years, and it's still kind of empty. So I understand.
You got a nickel. Come on, you got a nickel in there.
Unfortunately, the paperwork to get that nickel to Chris was just too much.
You need to run a telethon, Jason. All right. In the remaining time, let's see if we can get Josh Nimitz had a question there, and then winding things down with Joseph.
Yeah, hey guys, it's Josh with USGS National Geospatial Technical Operations Center. I work on 3DEP. Thank you for that presentation. It was great. You may have mentioned, and I might have missed it, but can you just share what the ballpark performance was like going from S3 to your supercomputer to recreate those digital elevation models directly from the point cloud for the entire state?
Yeah, I think so. We did it on essentially a county by county basis, I think we didn't run it on a supercomputer. We ran it on just a commodity cluster that's inside of the OpenTopo infrastructure. We've talked about doing this now for the rest of basically trying to scale up and compute more. And in that case, we would do it on HPC probably. I think it took a month or two of compute time. The Chelsea Scott who's at Arizona State on the topography team is the one who coded this up, and she was tweaking as she went. She was changing things and learning, and so I don't have a pure just exact time, but certainly it took a while, even on a decent machine. And a good chunk of that is the network time, is pulling the data back across from S3 to SDSC, and that is, as I said, there is SDSC has some agreement with Amazon, and they have some kind of dark fiber connection into US West that makes it go faster than if you didn't have that. So I think it would take a long time to do it for like the whole US, for example.
Yeah, that's helpful. Thanks, Chris.
Yeah, no problem. And if you, I guess I'll say this now since we're coming up to the top of the hour. Like, we sort of blasted a fair amount at you, but we're more than happy to have some sidebar conversations or offline discussions. If you want to follow up on any of these topics, feel free to shoot Matt or I an email, and could have another follow-up Zoom call or do it via email. But we're definitely interested in talking more.
Absolutely. Thank you. Appreciate that.
Howdy.
All right. Yep.
I work with Evan, and he introduced me to the USGS EPT tree, and it was wonderful to see that. But every time I try to write, a whole bunch of little JSONs to pull those tiles, some fraction of them just don't go, and it's repeatable. I mean, I can say, and they're interior tiles to, the full coverage. So it's not like I'm asking for a tile that doesn't exist. And I just had to give up and go to the user pays side, because I saw no way past it. You know, that there's no error message, there's no nothing to fix. And it's just like, you know, I've used the same code to write thousands of little JSON scripts, and some fraction of them just don't go. I'm wondering if I'm the only one that's ever seen that, or
Nah, I think Chelsea had that problem with some of the Indiana, and we had to, she got it from a different location. And I did notice they did change there at some point. They were changing field names in some of the JSON, and that kind of messed me up a bit. I had to check for, you know, changing of the field names.
But these would be like within a survey, within a single FEMA survey, some fraction of the tiles, just the map Mercator tiles just won't download.
Interesting.
But anyway.
Yeah.
Wasn't there also an issue, Matt, with the versioning of PDAL? There was something about the syntax of the EPT call that changed as part of a version update in PDAL, and it broke some of our stuff.
Yeah.
I remember us pulling our hair out. Being like, what the heck?
I mean, so whom should be complained to? Where would I complain if I'm, you know, wanting to pull all of them?
It's the Hobu GitHub site, because they're the ones and that's where generally with that for the PDAL one, I actually reported it to PDAL because I think it was a PDAL reading.
But I'm specifically having a problem with their EPT tree, so that would be Howard.
Yeah, and they're pretty responsive, so I would post to their GitHub site. There's a USGS-LiDAR GitHub site for Hobu.
Okay, thanks.
All right. Well, we're at the top of the hour. Matt, Chris, thanks so much for that. Thanks for all the participants and that kind of lively round of conversation. I think you can see the interest that you have. You've got the captivated audience, and we hope to continue this conversation. I certainly learned a lot. I've got a couple questions that I'd like to take offline with the OpenTopography folks, but thanks so much. Really appreciate that, and really appreciate ESIP hosting us.